and so on. But finally, the committee decided, ISA and IEC, to settle on the name Safety Instrumented System. The brief topics which I'm going to cover are listed in this slide. We'll be covering major accidents which happened and because of which this standard has come in action. Am I audible properly?
Yeah.
I found some crosstalk there.
Sir, you can be a bit louder, please.
यहाँ पे भी दिखाई दे रहा है। अगर इनमें से आप स्पीकर मोड चेंज करके टीवी पे ला सकते हैं। मैंने ट्राई कर लिया था, हुआ नहीं, इसलिए ये चला रखा है। तो इधर
requesting participants to just mute. Everyone just mute your mics. Yes, thank you.
Okay. So we'll have a brief idea about the major accidents because of which the regulations and the legislations in the various countries came into force to improve the life of the people and save it from the disastrous accidents. So some 34 accidents were reviewed by HSE UK for process as well as machinery industry. We'll have some brief on that. And the standards which came out of that, they are just listed over here. We'll discuss in detail. And then one of the important aspect I wanted to emphasize in this presentation is the training which IASA gives is little different quality-wise compared to the trainings which are existing in the country from many other competitors. I'll try to discuss this a bit more. Then the risk matrix, layer of protection, onion diagram. These are all the major points which will be elaborated during the presentation. One of the key points which I wanted to focus was SIS versus BPCS, which is a process control system, rather basic process control system. Now, both are protections layer, but the major difference is your BPCS cannot be allotted risk reduction more than 10, factor of 10, whereas SIS risk reduction factor ranges from 10 to 10,000. You can see the difference between the two. Why I'm telling you this to be more focused is because most of the chemical, petrochemical and process industries in India, including pharma, they do not go beyond BPCS, that is DCS based or PLC based or whatever single loop controller based or whatever way they are deploying. But in HAZOP also, they go on adding the additional transmitters, adding additional safety shutdown valves in BPCS. Now, this is where I think a little more focus will be required, and I'll try to elaborate in the presentation. Then general risk reduction concepts we'll discuss about, which every organization must have a risk matrix which they use after the HAZOP is conducted. Then very brief introduction of SIF, SIL and SIS, little elaboration on that because they are all interlinked. Then the failure modes, which are the required to be understood fundamentally. And then we'll go to the SIL tables, what is SIL 1, 2, 3, etc. means. And most importantly, the whole SIS is based on safety life cycle. So we'll have one slide on safety life cycle where we will discuss what are the various steps, ins and outs at the various steps. And safety starts, or SIS life cycle starts with HAZOP and risk assessment. So we'll try to discuss that point. And I think this should be more interactive in that particular point of discussion. Layer of protection analysis, we'll try to touch that topic. It's a qualitative type of analysis, sorry, semi-quantitative type of analysis compared to other type of risk analysis, which are qualitative in nature. In Europe, qualitative risk analysis is more prevalent, that is risk graph and risk matrix, whereas in America, it is the LOPA which is more prevalent. And LOPA has advantages over the other types, so that we will try to discuss. And again, I will try to re-emphasize that learning LOPA the ISA way, and we shall have a small example of LOPA so that people can understand that part of it. Not changing the slide. Yeah. So this is the point which I was trying to say. A disaster accidents occurred in the past, starting with most renowned Fixborough accident in UK, where all the people working in the plant, they met with death. There are 28 people, and it was a weekend, so the strength was less, fortunately, from that angle. The people in the nearby villages had to get evacuated, and more than 100 injuries were reported. The explosion was so blast that about 8 miles, the glass windows shattered, and the people there also had to evacuate. And fortunately, being a holiday, there are less people at the home and more outside the home. So fatality was not there during this particular incident. But this triggered the Health and Safety Executive UK to recommend industry by legislation to have a safety study of the plant, and they have to put the safety study to the regulators how they are going to address it so that such an event does not reoccur. Now, the second event which was major in those areas was that of Seveso, Italy. Now, this was a manually operated plant. Most of the plant in India, I'd say a small scale industry or medium scale industry plant, they are manually operated. And it was a similar in operation. That is why I listed it over here. In this plant, dioxin gas, which was a byproduct, nobody produces dioxin, such a dangerous gas. It does not have smell or color. But when it got leaked out, because on Friday afternoon, the reaction was started. When the reaction was started and when the reaction ended, it was an exothermic reaction, and the operator on the plant, he closed the steam valve, considering that now reaction is over and no more heat is required. But people did not understand the reaction can go in runaway mode also, slowly but surely. So what happened was, when he closed steam and everything, it was a manually operated plant, so he left the plant at 6 o'clock in the morning and waiting for the next operator to join at 8. In between, there was nobody in the plant. And there were alarms sounding, but there was nobody to acknowledge or do anything on that. As a result, these gas being so dangerous that ants and the people started dying after 2 days. This was a slow reaction of the gas leakage which affected the community, and so badly that about 2 lakhs of people got affected in that for that incident. As a result, the Seveso, it was in Seveso, so people gathered of the Europe together and they decided to do something about this. They came out with Seveso directive for every chemical or process industry. And this particular site of the plant is buried in the ground, and there is a garden at that location now. I'm just trying to get reminded that recently I saw on our TV that the incident of Bhopal, which is listed as 3rd place, now in this incident, now the number of deaths are 10,000. This is the old data. So it is 3,000, but as on date, 10,000 people have lost life in India because of Bhopal incident, and more than 2 lakh people are still affected and suffering from that. And the plant debris are still at the site. They are not removed. In fact, this is the sensitivity. I don't know whom to be blamed for, but nobody is ready to take that debris even to demolish completely. Like Siveso, they have a garden on that location now. Now this location is still suffering, and the surrounding environment is reported to be suffering because of the left out debris of the Bhopal plant. This is the condition as on date in India. And that is why this particular information of SIS or the knowledge of SIS is required to be spreaded widely so that such incidences are never getting repeated, at least in our country. Fourth is a Piper Alpha. Here it is on the oil and gas sector side, 167 deaths as it is seen over here. So in accidents keep on happening, but point is that people are not, sensitive, or the government does not take, steps so that it does not get repeated. Very recently, I read this in one of the news that in Andhra Pradesh, one of the pharma unit recently met with a reactor exploding and then fire on the site, taking 13 deaths. This is very recent, 22nd August 2024, just 2 days before. What I want to say is that people who are using hazardous chemical, who are reacting hazardous chemical, they should know there is something like beyond the HAZOP, there is some protections which are available. And if this knowledge is there, then probably we can reduce the risk of this type of accidents occurring. Now, this particular slide, I just wanted to say that in UK, they carried out a study of various failures, and the 34 accidents were then analyzed, and they found that these accidents have taken place due to control and safety system failure. Control and safety system failure, why I'm emphasizing this is, most of the chemical plant today are having DCS or PLC, because old days are gone where pneumatic instrumentation was there, and safety interlock panel used to be electrical panel, and it used to be relay-based safety interlock panel. I've been working on that in late 70s in GACL, but nowadays everything, most of the plants are having DCS or PLC or some sort of computerized system, where safety and control systems are combined. Now, safety and control system, when you combine, as per the standard, it does not really improve the performance of the safety. That is why the failures are analyzed, and these 34 accidents which were analyzed, they found that 44% of the accidents were due to incomplete or incorrect specifications. So this is the area which needs to be focused when you order any instrumentation, whether it is for BPCS or SIS, that you have to focus more on the correct and complete specification, because once it is correct and complete, then the chances of its failure are widely getting reduced. Okay, so for example, if you are selecting a pressure transmitter of very renowned brand, and even if that transmitter has been selected which is having a highest level of performance, now level of performance in terms of device are rated as SIL 1, SIL 2, SIL 3. Let us say it is a SIL 3 rated transmitter which is selected for a chlorine, but chlorine with little moisture can affect even if it is SS. So right diaphragm selection for the pressure transmitter for chlorine is not the SS SIL 3, but it should be tantalum or monel. So if you are selecting a wrong, specifying a wrong transmitter, for material of construction which is going to come in contact with the process fluid, probably even your CL3 transmitter will fail in a day. It will not take more than a day to live life. So that is why complete and correct specification is a must, considering its application, and that is to be decided by the people who are building the plant, who know their process and what to select and not. So second level of this thing, failure was at 20%, which came after changes of the commissioning of the plant. I have observed in many industries, P&ID what is given at the time of installation of the plant, it is hardly addressed later on. But you do a lot of changes later on to suit either production or suit safety or quality, many reasons. But no P&ID gets revised. As a result, in a long term, the person who is attending the plant after 10 years of the erection of the plant, he doesn't get the clue. And if he does some changes which is not recorded, which is known as a MOC, that means management of change system is not being followed, then that can lead to the accidents. This is as per the survey what has been done. Installation commissioning is 6%. Operation and maintenance, I'll give you an example that if you are taking out any sensor or the control valve for calibration purpose or doing calibration there, but if the mistake is done during the calibration by the instrument technician or the foreman, whatever he may be, then that type of mistakes has led to 15% of the accidents. Operation point of view also, in BPCS, normally on DCS base, any controller, operator is free to change the mode. He can change the mode from auto to manual. If he finds that in auto mode the controller is not functioning all right, he will take it to the manual one, he will try to control it. And in that process, if he forgets to change back to auto mode again, then the incidences have been reported to result into disaster accidents. Now, this type of analysis, once it is done, the standards which are made are taking care of those things. Now, which are the standards which are made? Now, these are the major standards. First standards which came out by European Community, it was in 1998, that is IEC 61508. Now, before that, ISA has come out with the ISA 96 standard. And ISA 96 standard was in 1996 prior to this. But after looking at this standard, ISA also reviewed it, and then they decided that we can adopt this standard after doing some changes which are required as per the American legislations or American acts like OSHA and EPA. So IEC 61508 is known as a mother standard and or umbrella standard, and this is in 7 parts. Mainly it is more focusing on the products like transmitters, control valves, logic solvers, etc. And so mainly the vendors or the manufacturers of the devices, they follow IEC 508 standard, and they have to see that it is certified as per IEC 61508 standard. Later on, the standard is very open, and many other sectors like a process sector, which we are going to discuss more in detail, have developed a IEC 61511, which is applicable to process sector, and this is applicable to process sector. And this was the same standard which I mentioned that ISA generated a standard in 96, but later on ISA also generated a ISA standard 84 in 2004. Now in 84, ISA 84 and 61511 have identical clauses, absolutely identical clauses, except some addition because of this prevailing regulation of OSHA and EPA in America, which were then in ISA 84, but not then in ISA 61511. But now, as on date, ISA is in totality following IC 61511. They call it ISA IC 61511. So we'll discuss more about that. Now, same way, there is a standard on nuclear system which is 61513, and for the machinery sector, ultimately it is also derived from ISA 61508, and it is a 62061. Lot of similarity may be there because all the three standards are derived from 508, and there are a lot of similarity in these standards because they are derived from the same root. Coming to telling something about the ISA. When you take an ISA SIS training, this training is not just collection or gathering or presentation of the slide, which may be 100 or 150 slides by the other competitors. I'll not name it, but the people who are training for 3 days or 4 days, and then fifth day they take the exam. That exam is based on only the slides, understanding the slide study. It doesn't give you any deep dive in the subject. Whereas in ISA, the methodology is totally different. Here, the time you register for ISA, ISA training is divided in 3 parts. First is the fundamental training, SIS fundamental training, and that is for around 4.5 days. There is a separate book written for that, exclusively only for appearing in the exam, which has got 550 pages, only the book. And this ISA standards, that time when I appeared in the exam in 2011, it was 84, and 61511 was not existing that time. Though ISA had adopted 84, he is writing in the bracket, ISA 615-1 mod means modified. So they do carry out some modification. So in short, when you take any ISA training, it is something other than the classroom slides and the discussions and the training. You have to study the material which is given to you as a study material. Particularly the standards, they used to share the standards as a part of the training. Hard copy of these standards were shared. Now they are sharing the soft copy because ISA has stopped now printing the standard because they have adopted IEC 61511 as a standard. So it is now ISA IEC 61511. But the cost of this standard is very, very high. If you want to buy a copy of ISA 61511 3 parts, it will cost you somewhere around $1,100. Nobody can afford that, particularly at an individual level. So, but during the training, they make all the trainee to have access to this standard. These standards are not accessible even to ISA member, ISA 61511, okay? Because you have to pay royalty to IEC for that. Anyway, apart from that, since they have made it available, and I have got these standards available, but for Indians, one good thing I'm going to talk, the same standards are available in Indian rupees at much cheaper way. And the book which I have listed here is a book for the second level exam, which they call it Safety Instrumented Level Selection. And this, the people who pass the second level exam, they are known as Safety SIL Selection Specialist. I have passed that exam way back in 2018. So every course they give one book and a copy of the standards to study. Okay, either they are sharing to the people also who are registered for this study to have the standard available as long as they want, because it's a cost. The cost of ISD training is, that is why shooting was so high, it's not affordable in India. It for first $1,800, okay, and subsequently it is $1,650 for each. So total cost will not be less than $6,000, okay, for the getting trained for ISA, which is not affordable in India. So I decided, at least I have completed the course, why not to share whatever I learned during the ISA. Okay. Now before proceeding further, these are some basic definitions which are important to be known to people even in today's presentation. See, some basic definition is safety as per, here let me also tell you that India has come out with ISIC 61511-1 2017. This is same as IEC 61511-1. Okay. But India adopted this and printed in 2019. Now this standard, it is in 3 parts, it is available, and all the 3 parts cost is around 4,500 rupees, and it is published by Bureau of Indian Standard BSI, and that is why I am telling you it's a good news, at least for the organizations or the companies. 4,500 is not a big cost, but you should spend money to have this so that people can refer, just like a Bible, that what do they want to understand, or the terminology and the details and the illustration. Standards is in 3 parts. First part is normative, which is mandatory. Second part is just explanation. So you have to read first and second part together, same number of clause in first part, and look at the second part so that you will understand. It will explain with the example in the second part. Third part is exclusively for the SIL selection, which gives you the methodology of how to select the SIL by risk graph method, risk matrix method, and the LOPA method. So this is how it is. So I hope that this information is very useful. Anybody can get it from visiting the BIS website also, or BIS Delhi office. The hard copy is as well available. They give you soft copy, you can print out the hard copy out of that. So here the safety is, you see how it is. Earlier when it was defined safety means freedom from unacceptable risk. Now when it was changed in 2016 standard or 2017 standard, it is changed to risk which is not tolerable. According to ISO and IEC Guide 51, both are same, whether you call it freedom from unacceptable risk or you call risk which is not tolerable. It is one and the same. Safe state. This needs to be little elaborated. Our understanding in general is you shut down everything and it is safe. Now, shutting down everything is not the safe state as per the standard. Safe state of the process is when safety is achieved. That means in some processes, you cannot shut down. Can you shut down aircraft if you find some fault in the safety system of aircraft? If you shut it down, okay, what will happen? It cannot ground safely. So you don't have to shut down everything, but there are recommended practices and you have to define what is the safety in case of automated safety system fails. In automated safety system fails, then manually pilot will drive it to a safe place to land. So this is what is to be defined as a safe state. So for equipment like a gas turbine, when gas turbine is required to be shut down due to XYZ fault in the turbine, but still the lubrication system of the gas turbine has to keep running. So safe state is not always shut down. Safe state means something which is defined by you as what is a safe state. So one has to define safe state very clearly in chemical processes also. I have come across chemical reactors where the reactor, if you stopped the agitator, the internal mass, which was a liquid, it will solidify. So you have to keep the agitator running. You shut down the feed to the to the reactor. You shut down rest of the things before coming into the reactor and going out of reactor. But you cannot shut down the stirrer of the reactor because it will make a gel and your stirrer will fail to work when you want to work it again. So that is why safe state needs to be understood. It needs to be defined by every process and by every equipment. What is the safe state of that? Now, third is a safe failure, which does not have potential to put the SIS in a hazardous or fail to function mode. Now, safe failure means that it's in other way, the note written here in the standard is a nuisance failure. Sometimes the plant trips, sometimes your laptop goes blank. You don't know why. When you don't know why, but it still fails, maybe it is a safe failure. Maybe it is a safe failure. You may be able to restart it again. Okay, but you do not know. It is a safe but undetected failure. Failure is detected because it has failed. So you detect the fail, but why it has failed is not detected. So it is a safe but undetected failure. So the failure happens that to be a safe failure, it may be detected or undetected. So such a type of failure is known as a nuisance failure. Such nuisance failure is not always welcome because you'll be losing the production. The plant is getting shut down just like that, and you don't know the reason why it is getting shut down. One has to analyze the reasons of the safe failure as well. Okay, so other terms which are for the safe failure are nuisance failure. They are known as a spurious strip failure or false strip failure or fail to safe failure. There are various terms used for the same failure. These are as per the clauses, as per the standard. I have not added any words or removed any words from that. And most important now is the dangerous failure. Dangerous failure is the failure which disables given safety action. That means it does not, safety action will not take place if there is a dangerous failure of a device which is a part of the safety system. To give you an example, suppose you have a level transmitter and level transmitter fails dangerously. That means you do not know whether it has failed or not. Had you been knowing, you will definitely remove and replace the transmitter or repair it. But you do not know. So what you do not know, and if it fails, and if it fails dangerously, that means that level transmitter was supposed to give you an alarm for the high level in the reactor, and the transmitter has failed and doesn't give you an alarm for the high level. It's a dangerous failure. The dangerous undetected failure. You also do not know whether transmitter has failed or not. So for dangerous undetected failure, if it is a single transmitter and if it is fails in a dangerous mode, you will lose the safety with respect to safety instrumented function or safety instrumented system, whatever you call it. Okay, but dangerous failure are the one which are concerned. It is not important to know how the system operates or how the system works. It is more important to know how the system fails. If you know how the system fails, you will succeed. If you know how you are failing yourself in many of the aspects, probably you will succeed. You will make a success. So it is important to know when you fail, how you fail, to address that you do not fail next time. So this is the same philosophy applicable here, that then it is important to know how you fail. Now, risk is very important word, and the whole standard, everything is based on this particular risk, this word. That means risk is defined as a combination of likelihood and severity or consequence. That means how bad is the risk? For example, I give you an example which is easy to understand. There was a earthquake in Ahmedabad way back in, I think, 2002 or so. Now, this was severe earthquake. Many buildings had collapsed. The locations are now known as, just a sort of to remember that this location, the building had failed. Mansi Tower, we call it, one of the tower, huge building collapsed because of the earthquake. But this incident, how likely it is to happen again? You do not know, but it's very less likely. So risk of earthquake frequency is very low, very low. Maybe it happened in Ahmedabad once in 100 years. Maybe another 50 years it may happen. Kutch was totally demolished during the earthquake. It is re-established again, but now the buildings, people have been wiser that they have made the building construction which can withstand the earthquake to some extent. Earthquake of the order of Richter scale 5.7 or something like that. It's a norms of government. So, and how severe is that harm? The harm which occurred in Bhopal, can we tolerate even once in 100 years? It cannot be. So the risk is to be defined as to how severe it is. By the way, the Bhopal incident so far was the largest in the world, in the history of the world, in a chemical plant. Another term which comes to be understood is a tolerable risk. Tolerable risk as per standard is risk which is accepted in a given context based on current values of the societies. Means what is tolerable? What is tolerable to the people of a plant, working in the plant? That is working in the plant owners. Actually, who decides the tolerable risk? Tolerable risk is to be decided by the management of the company. They have to decide what is tolerable risk for us. So for an example, tolerable risk for a company of 1,000 people, okay, maybe company top management sits together and decides that probably we can have one fatality out of 1,000 people per year. Okay, this is a decision of the company top management. That means 1 in 1,000 per year, if dies, company probably consider that as a maximum risk which is tolerable. So that means 1 in 1,000 per year is accepted tolerable risk by that particular company. And the safety system will be designed based on tolerable risk. If a company like Reliance, where 10,000 people are working, they will say, no, in my company, in my reputation, I would like to have 1 in 10,000 people dying in a year, probably I can accept. If somebody says that no risk is acceptable, it's a zero risk, I said it's a vague definition. If your company has decided zero risk, if some accident occurs, are you closing down your company? You are not. You are not closing down your company like Bhopal. Okay. So it's no point in saying that zero tolerance for the fatality. It is a vague definition or vaguely defined term as a tolerable risk. So a company, I've seen a company that where 10 people died, 7 people died, 4 people died, every 5 years, they are still running. That means it is a tolerable risk for that company. You are not closing down your doors and going out of business. So tolerable risk is varying and is to be decided very precisely by the people of the organization who are the top management. Another term which is defined as a process risk. Now, process risk is the risk arising from the process condition caused by abnormal events, including BPCS malfunction and human errors. Now, this also you must understand. See how difficult it is just to read the standard. You will not get into the details of it unless somebody explains it. So that is why ISO standard part 1 is only the normative or mandatory. Such definitions and such chapters are given for understanding the process safety, but they are elaborated in part 2. And part 2 explains you more detail with examples. ISA has come out with technical reports to the extent of tier 9. And these technical reports explain you much more in detail about what is to be thought about or what is to be done about process risk or tolerable risk. And that is why a volume of information is available in ISA, which is required to be run. And when you pass the examination, unless you have read these volumes and unless you have read these standards, probably it will be difficult for you to pass. But it's not difficult also, it's very easy. People who have got 10 years of experience and they take this course, I'm sure they will definitely pass it. My student in India, which we conducted ISS America's course at 50% cost way back in 2021, and out of 10, 7 people appeared in the exam and 6 have passed. They were all from the field. And you can understand our understanding of the standard, our understanding of the material given in the books and the standards based on which they pass the exam. These exams are not difficult at all, but one needs to read it, do some effort. Not that you take course of 3 days, the 4th day you appear in the exam and you say, oh, I'm certified process safety engineer of so and so. That is, I would say, very bluntly, a nonsense. You'll not be able to really understand. You have understood only the slides to the extent. Can you understand this course which has got 770 pages in 3 days? I doubt it. Okay. Anyway, now coming back to the topic, the next definition is SIF. It is a safety instrumented function. It is defined as a safety function to be implemented by safety instrumented system. So easily defined. So SIF and SIS are related with each other. If safety instrumented function, many safety instrumented functions are there, then it is known as SIS. The process plant can have a SIS where many SIFs will be there. Many safety instrumented function will be there. We will discuss or give you more detail when you go further. So these are the one-line definitions as per the standard. SIS is defined as instrumented system used to implement one or more SIFs, as I mentioned. And what is SIL? SIL is a discrete level 1 out of 4 allocated to SIF for specifying safety integrity requirements. That means to be achieved by SIS. That means 1 out of 4 means there are SIL 1, SIL 2, SIL 3, SIL 4. This is what I have elaborated by RAID. So it can be SIF which will be assigned. SIF can have SIL 1, SIF can have SIL 2, it can have SIL 3 or it can have SIL 4. In short, these are the various levels assigned to SIF. Higher the risk, better performance is required by the safety system. The safety system is implemented for the safety functions. And safety functions are implemented by SIF, means safety instrumented functions. So every safety instrumented function needs to be specified what level of performance you are requiring out of me. That means if I'm SIL 1, I'll have some type of hardware, some type of architecture, some type of devices to be part of my instrumented function. So in short, each SIF is having a specified SIL. There is no SIF which is without SIL. It is just like a control valve. You say that you want to put a control valve and it will be a regulating type of control valve, but you do not specify what will be the CV of the control valve or coefficient of variation, coefficient of volume for the control valve. So if you don't specify CV of the control valve and you say you have specified control valve, it's a wrong specification. It's inadequate specification. So every control valve, like CV for control valve, is a part of the control valve specification. SIL is a part of the SIF specification. I hope it is clear. Every SIF has a SIL, but every SIL need not be a SIF. I explain this why. A transmitter which is capable of SIL 3 is not SIF. Is a capable of giving you performance of SIL 3 level, but it is not SIF. So SIF has got SIL, but SIL does not have SIF. SIL does not give SIF. SIL can be for transmitter, SIL can be for control valve, SIL can be for logic solver or PLC. Safety PLC is having a SIL rating, SIL rated 2, SIL rated 3, etc., etc. General purpose PLC does not have any SIL rating. So for safety application, you have to go and deploy a safety PLC and not general purpose PLC or general logic solver of BPCS. That's all. Next. Here, whatever we have defined here, this slide indicates very pictorially the same thing. Process risk is at this level. Now, this risk includes the risk of BPCS failure also, like I have written here, abnormal events including BPCS failure. So from this risk, this is the level of your tolerable risk, which we discussed. Okay. Now, if you want to go from process risk to this risk, how can you go? You can go by protection layers. Protection layers, SIS or SIF is one of the protection layers, but there are other protection layers which will follow in the slides, okay, which can reduce your process risk to a risk more than even tolerable risk. So these risks are reduced by the layers of protection. So this is a slide which indicates process risk, tolerable risk, and residual risk. Residual risk means a risk which now onwards you don't have to bother. It is acceptable risk. The likelihood may be very high, but you don't mind because the level of risk is so low that it's okay. Now, this is a slide which is taken from the book, which I showed you the picture of the book. This is known as an alarm principle. Alarm means as low as reasonably practical. So this slide, based on which people are going to design the SIL level. That means at this, above this level is not tolerable. Risk cannot be justified on any grounds. That means if you are in this region, you cannot run the plant. It is not acceptable to management or to the people, and you have to reduce the risk. Once you reduce the risk, because this is the maximum level of it, this line is the maximum level of risk. When you reduce the risk below this line, then it becomes acceptable region. It is from this to this, all is acceptable region, means risk is tolerable. It's a tolerable region. And when you go below this line, this is the minimum risk. This is minimum risk, this is maximum risk. Below this risk is not required to be reduced because it is broadly acceptable region. So our SIF, our SIS, everything should be designed for this region, that is LOPA region. As low as reasonably practical. But what is meant by as low as reasonably practical? This is a verdict given by the court of UK that you cannot tell when the cost of the whole plant is, say, for example, whole plant is costing you 10 crore, and you say one SIS will cost me 3 crores. It is not practicable. It is not even, it is more than the profit I'm making out of the plant or out of the project. So again, a cost benefit ratio is to be calculated. And when you go below minimum risk, it is tolerable if the cost reduction would exceed the improvement gain. That means it is a negligible risk, and if you spend for the safety, probably you are losing the money, you are not gaining any money. Ultimately, people will adopt a safety systems or safety standard where they reduce the high risk to a tolerable risk, not from tolerable risk to broadly acceptable risk. But in tolerable risk, if it is cost effective, this is what is written. Tolerable only if risk reduction is impracticable or if it cost is grossly disproportionate to the improvement gain. So you are gaining from making the system SIF from SIL 3 level, from SIL 1 level, but the cost which you will be spending to make it SIL 3 level is so high that probably you will lose all your profit. So government or court of law has said it, make it as low as reasonably practicable. Make it SIL 1 is reasonably practicable to accept SIL 1. Making SIL 1 to SIL 2 is costly. It's a cost. For SIL 1 system, you may need single transmitter, single logic solver, and single final control element, which are the three major elements of a safety system. But for SIL 2, you may need a 2 transmitter. For SIL 3, you may need a 3 transmitter and 2x3 logic. It makes design much more complicated. You have not only to select the design, you have to maintain also. So it will be a costly, life cycle cost will be very high for SIL 3 rated SIF systems or SIS systems. Here is a practical example of giving you risk matrix. This is a risk matrix, which is combination as defined the likelihood and severity combined. Now, likelihood is categorized in 4 categories. This is the highest likelihood, means very likely to happen is the highest likelihood. This is the lowest likelihood, 1. Similarly, severity is also categorized in 4 categories. This is least severe, this is the most severe. And in this matrix rectangle, this region is 14, means 4 into 4 makes 14. So this is this rectangle or this square is the one where risk is maximum. And this is the one where risk is minimum. One would like to travel from maximum risk to minimum risk. But again, in between that, this A means LRP region. LRP, we discussed the concept as low as possible. You can go from highest level of risk to as low as possible region, and which is economically viable, to a medium risk level, and design your SIS accordingly. And no low risk level region, don't have to do anything further. Okay. Now this is a risk matrix. Now risk is not only for safety, it can be for equipment, it can be for production loss, it can be for environment. So these are the all consequences. 4 types of consequences are described here, and probability of happening, likely, unlikely, very likely, extremely likely, are shown in this risk matrix. one would like to work in this region, in the yellow region or green region. But risk needs to be classified, and this risk classification is done after the HAZOP. Now, this is the most important slide in that sense that this indicates that what are the protections layers. You are able to reduce the risk because of the protection layers. First of all, to start with the process itself, when you design a process, you should design a process which is inherently safe. Inherently safe means, I give you an example that heavy water project at Vadodara, heavy water unit project at Vadodara in 1976, they had a process of very high pressure, 180 bar pressure and temperature of 300 degrees centigrade to make the heavy water. And they were, in those days, there was no DCS PLCs. So they used to have a relay-based safety interlock system. Okay, and from that process, as on date, now they've brought the process changes, made inherently safer. Means now the process is working at a low pressure, manageable process, maybe 20 bar pressure, and temperature maybe say 200 degrees centigrade. And the process, this is known as an inherently safe process. Same product can be made by making the process inherently safe. I give an example of chloralkali. In 76, when I was working in joint GACL in 76, that time there were mercury plant and mercury electrolyzers were there, where the risk to the human were very high because of the mercury vapor. Now the process has changed to membrane electrolyzer. No more mercury is used anywhere in India in any of the chloralkali plant, though it is used in Germany and America. You will be shocked to know that. But in India, all the plants are now membrane-based plant. So process should be selected which is inherently safe. That is the first layer. Second layer is BPCS, as we mentioned, basic process control system. Third layer is alarms and intervention. Alarm does not do any work other than cautioning you by flashing light or a horn. It doesn't do anything other than that. So that is a third layer, but it has to, every layer has to be an independent layer. Okay. Independent means BPCS will not depend on alarm layer. That means you have to have not alarm derived from the same transmitter which you are using for process control, but a separate transmitter and separate alarm system for alarms. Then it is a safety layer. Then the fourth layer is SIS, which we are all talking about. SIS is a very flexible layer. You can have this layer designed for SIL 1 performance to SIL 3 performance for the process industry. So this takes care of whatever is not addressed. If process fails, BPCS takes care of it. If BPCS is functioning all right, how many of you believe that your process control system or controller can never fail? If you have that thinking, it's a wrong thinking. Process control can fail. Second layer, operator intervention, operator can also fail because operator is a human. He can also fail. And then SIS can also fail. So let me give an example of SIS. If SIS fails, we need a separate protection layer for the pressure. Say, for example, if you are addressing a process control, or you have to maintain a pressure in the reaction or in the reactor or in the equipment to a safe level. If all the three level fails, that is BPCS fails, operator intervention with alarm fails, SIS fails, you have to install a process safety valve like in boiler. Indian government has a boiler act. Every boiler needs to install a 2 safety relief valve on the boiler. This is the fourth layer of the protection. But the first four layers are known as a prevention layers in this diagram. And after the fourth layer, they are known as a mitigation of them. They do not reduce the risk, but they mitigate the risk. They do not prevent the risk, but they mitigate the risk. That means if you are having a dike on a storage tank of a hazardous chemical or a volatile flammable chemical, it serves the purpose, but it does not remove the liquid which has come to the dike. So it is still, risk is reduced, but risk is not prevented. So all those layers are prevention layers. Now plant emergency response, community emergency response, these are all prevention, mitigation layers. In case of Bhopal, people did not have knowledge that when the gas, methyl isocyanate gas had leaked out, that gas cannot pass through the wet cloth. So if people were given just a direction that use the wet cloth and then breathe it, close your eyes and put the wet cloth and then breathe it, that would have saved many people. Lots of people's life would have been saved if this simple response was available to the community. How to respond to the gas leakage. The community is taught, plant people are taught, then the reduction of risk can take place. This is all what I wanted to say. So SIS is composed, focus is going to be SIS, is composed on any of the combinations of sensors, logic solvers in the final elements. You see, you can have 2 sensors, 2 logic solvers, 2 final element, 3 final element, 3 sensors, 3 logic solvers. Depends upon what level of SIL is required to be established out of this. Now, let me clarify here that process industry standard defines only up to SIL 3. SIL 4 is not applicable for the process industries. Okay, it is applicable to the nuclear industry or maybe other industries. Now, what is IPL? You know, I mentioned to you that each of these layer has to be independent of each layer, each one. So IPL, that means each layer has to work as a independent protection layer, not IPL cricket. Okay, here SIS is an independent protection layer. BPCS is also an independent protection layer, and LMI and operator is also an independent protection layer. But here the standard defines that IPL should reduce minimum risk reduction by a factor of 10. By factor of 10, 10 is what? 10 is probability of failure, 1 upon probability of failure. That means probability of failure is a 0.1. Is 1 upon 10 is the probability of failure. That means what I mean by this is, suppose there are 10 devices or 10 control loops. Now, out of 10 control loops, per year, if one fails, then it is known as 1/10 per year failure of the control loop. That means 1 out of 10 control loops fails in a year. Now 1 out of 10 is 1 upon 10. If you probability is 1 upon 10, if you inverse that, it becomes 10. So risk reduction factor is inverse of probability of failure. So risk reduction, every protection layer should give minimum risk reduction of 10. That is what is defined as per the standard. Now there are other things also. Specificity, independence, it should be independent, it should be dependable. That means you can rely on it. It can be counted on to do what it was designed to do. And auditability means you should be able to audit it. Okay. Now I'm coming to this next slide, and there I will explain you what is auditability. Now here, this is a diagram where it differentiates BPCS and SIS. Now I think there will be a time constraint. probably I'll not be able to go through the complete presentation, but whatever fundamentally I wanted to give you a glimpses are good enough. Now in this slide, it indicates diagrammatically BPCS and SIS. Now BPCS, if you look at this, BPCS is a system where transmitter is there, control valve is there, which is a regulating valve. This is not on-off valve. It will regulate. The sensor is connected here, pressure sensor is connected here, and then you have to control the pressure depending upon the requirement of the pressure control. Here is a valve which is connected here, and the flow is being controlled by BPCS. As long as BPCS is functioning all right, process is safe. You are in the safe state of the process. You have given a set point, and BPCS is controlling this control valve and maintaining the process parameter around the set point. But what if this BPCS fails? BPCS do fail, and most of the accidents which have occurred, major accidents, they have occurred because there was no SIS separate. Now in this diagram, standard says you should go for a separate safety instrumented system. Separate system means separate transmitter to the input of the system, separate output to the final control element, and here the final control element is solenoid operated on-off valve. It is not a regulatory valve. So this is independent of BPCS. This system will work independently. This system will work independently. Means suppose this SIS fails, then also your BPCS can continue to work. SIS can fail. It is a transmitter. It is a solenoid valve. Solenoid valve can get stuck up. You are using ultimately air. Air can have debris and probably moisture, which can make solenoid valve to fail, and then SIS can also fail. So SIS can also fail. You remember that thing. The only thing is SIS has a flexibility that you can have higher level of SIS. Instead of SIS of SIL 1, you go for SIL 2 or SIL 3 maximum. It will cost you money, but you can have a higher level. So it's a flexible way of addressing higher level of risk than simply which is being addressed by BPCS. Now people, instead of connecting this transmitter from interlock, if they connect here, the same transmitter they connect to BPCS, and then output they give from the BPCS, then the BPCS does not improve the safety. If you want to improve the safety, it improves the performance of BPCS, and standard says that you cannot get credit more than risk reduction factor of 10 for BPCS, and that is why you have to go for SIS if your risk level is high. Okay, so SIS is also composed of sensors, logic solver, and final element. But the quality of transmitter used here is much better than the quality of transmitter, this is a general purpose pressure transmitter. This is not general purpose pressure transmitter. This is a SIL rated, SIL capable transmitter, maybe SIL capable 2, SIL capable 3 transmitter, which goes to a logic solver, which is also certified for SIL 2, SIL 3 rating. And output of this does not go to ordinary general purpose solenoid valve. It is a SIL rated solenoid valve. SIL rated solenoid valve will cost you fortune. Ordinary solenoid valve may be 4,000, 5,000 rupees. This may be 60, 70,000 rupees. So don't go for every safety requirement SIL 3 and end of it. SIL 3 will cost you heaven, and you cannot afford it. So that is why you have to have a SIS study, SIL study, risk study, and then you can proceed further. Okay. Now, safe failure and dangerous failure. Safe failure are the failures which are visible. Initiating means which are visible. Overt means obvious. this can be spurious. As I mentioned, plant tripped. You don't know how it tripped. Everything was normal, but it still tripped. So it is a spurious trip. But when the plant trips like that, you have a costly downtime. You lose the money. But in case of dangerous failure, it is inhibiting. That means it's not so easily visible. It's not obvious. Okay, it is hidden. Potentially, it is dangerous. That means it can lead to a big disaster. That is why it is dangerous failure can lead to dangers. Means your level transmitter, even if it is SIL rated, if it fails, it is a dangerous failure. And how can you find? BPCS, as I mentioned, is a dynamic. BPCS is dynamic, whereas dormant SIS system is passive. It is not dynamic. This is dynamic, this is passive, but it monitors the parameter and takes action when required. So it is passive but dormant. Whether it will take action or not, you will know only when it crosses the set limit. In this case, it is obvious when your control valve is not functioning, you can see control valve is not functioning. Here the control valve will remain in same position. If safety condition wants it to remain in open condition and close when parameter exceeds, this will remain open. And if control valve remains open for many time, long period, it may get stuck up. It may not work. So that is why the only way to find out the dangerous failure is you must test it. So every SIS system, every SIF system needs periodic testing, which is known as the proof testing. Now, this type of thing, dangerous mode, undetected, safe mode undetected, detected, undetected, but dangerous mode failures are, if it is happening in the SIS, you need to periodically test it. So this SIS is a dormant and passive system. BPCS is active and active and dynamic system. Control valve is dynamically moving. So it's an active and dynamic system. This is the basic difference. I think probably we may be running out of time, and whatever I have given to you was the most fundamentals of the SIS. Probably time is running out of this. Let me leave it for some time for the question and answer. So whatever we have shared, you can enjoy asking the question, and I'll answer your questions. Hello?
Yeah.
Am I audible?
Yes, now the forum is open for question answers. Thank you, Pramod sir.
Hello, sir.
Yes.
I have to answer those questions for the how are the safety instrumentation system applied in medical instrumentation?
In medical instrumentation, there is a separate probably norms for the medical instrumentation. These standards are silent on the medical instrumentation applications, but you can have consideration that you go for, when you select a sensor for the medical instrumentation, you go for the specifications of the sensor and ask for the failure rate by the manufacturer. If the manufacturer gives you the failure rate of the sensor, you will be able to judge that whether the system will fulfill the requirement of medical science or not. But as on date, there may be a separate standard for the medical instrumentation. The SIS cannot be applied for the medical instrumentation.
Okay. Thank you, sir.
Sir, what is the difference between SIL verification and validation?
Yes, SIL validation, because I'll show you the slide. Unfortunately, I could not go through. See, in this slide, verification, can you see my slide? Verification.
Yes, sir.
Yes, sir.
Verification is applicable all throughout the safety life cycle. You can see this block. It's applicable. So every stage verification, you verify hazard and risk assessment, whether it is done properly or not. You verify whether allocation of safety function is done properly or not. You verify whether you have designed the system properly or not. So verification is applicable to each and every phase of the safety life cycle. Whereas validation, you can see here, installation, commissioning, and validation. Validation is applicable only after the plant is going to be commissioned. That means before the plant, you take the chemicals in the pipelines and the reactors, you validate that whether your system is as you wanted or not. I give you an example of an automobile. Say an automobile industry, a very good pickup truck was built, good brakes, good cabin for the driver, air-conditioned cabin for the driver, and very nice, so it can take so much of load very easily. Very nice pickup truck was built. But when it went for the final validation, it failed. Every stage it was checked. Steering is working all right, tires are okay, brakes are working okay. But it failed because original specification wanted it to be a four-door sedan and not pickup truck. So what happened was you have made a pickup truck, but it cannot get validated for the requirement of a sedan. So this means validation is whether the safety system which is written in the safety requirement specification. You can see here, safety requirement specification are to be specified as one of the safety life cycle steps. Now, if the safety requirements specification are not getting validated before commissioning, it fails in validation. Validation is to be done against the safety requirement specification, and it can fail. Whereas verification is to be done at each and every phase of the safety life cycle. So verification for each and every phase, whereas validation is only for checking whether the system which is designed and being commissioned is meeting the safety requirement specification or not. I hope I'm clear. Is
Yes,
that
sir.
clear?
Yes, sir. Yes, sir. One more question, sir. There, after how many years we require to recheck the SIL level of any plant after the commissioning?
I would say that SIL level reaching is whether you have designed your plant to the required SIL level or not. That is important. What is the level of risk? Okay, SIL level is not to be reached due to aging, but SIL level is to be decided based on your based on your hazards. Okay, if you have got high hazards, you know, say for example, if you are in, let me go to that graph. If you are having a high hazard, and if you are in this level, that your likelihood happening that hazard is very high, then you have to design your system so that your risk is addressed. What is SIS is doing is SIS is reducing the risk beyond BPCS. BPCS alone cannot reduce the risk. When your BPCS alone cannot reduce the risk, you go for a separate independent system. And maybe SIL 1 also will be okay for the lifetime of the plant. You don't have to go to always SIL 2 or SIL 3 design. So it all depends upon proper HAZOP. During the HAZOP expert has to tell, during the HAZOP expert has to tell whether you require SIL or not. Okay, so HAZOP and risk assessment is the first stage where you decide whether you need SIL or not. Now, all the process loop do not require SIL. Only a few process loop may require SIL. And if your plant, you are not handling any flammable chemicals or hazardous toxic chemicals, maybe you don't require seal, but that is to be decided at the first stage of the safety life cycle of SIS. Am I clear?
Yes, sir. Yes.
As the plant leaves, in fact, suppose you are installed SIL 3 level of system when the plant SIL 3 was required and you installed SIL 3, but you are not doing any proof testing like I mentioned. So if you are not doing proof testing or not periodically testing, your SIL 3 can get deteriorated to SIL 2, SIL 2 can get deteriorated to SIL 1, it can give you 0 level also. A plant with SIL 3 rated but not tested for 5 years, it will give you 0 SIL performance. Or SIL is a performance. Your SIL 3 performance will get declined to SIL 2 or SIL 1 or SIL 0 if you are not periodically testing, because your SIS is a dormant system. Your control valve which has not operated for 5 years and was in open condition in a normal plant running. And when you want to operate it, it may not operate. So that means your SIL 3 rating has gone to SIL 0 rating. I think probably I tried to answer you in your way also.
Yeah, re-verification and recheck is depend on the SIL level.
SIL level, right?
Yes, yes. One more, sir. SIL, two methods are there for the SIL analysis. One is that race matrix, and the second is LOPA. So where we use to which type
I
of the
tell you,
method?
LOPA is a semi-quantitative risk analysis. It is giving you precise result if you do analysis by LOPA, whereas risk matrix and risk graph, they are qualitative methods. In qualitative method, they are more subjective. If someone is doing qualitative analysis of the risk and he wants to derive the SIL, it is the expert how strongly he takes the stand. Sometimes the experts are very adamant. He will say that no, this risk is very high. As per me, 5 people will die. How can you say 4 people will die? Okay, then probably you will end up in a high SIL rated system. Are you getting my point? And this is a qualitative analysis because there is no figure. Whereas in LOPA, it is a semi quantitative analysis. Your consequence is subjective. Risk is high, severe, very high, intolerable. Okay, these are all qualitative assignment to the consequence. But the probability of failure of the devices in the system, they are based on the quantity data, quantitative of failure data, maybe the maintenance data or the manufacturer's data. Best is the maintenance data. If the plant is having a data of letting you know that there are 200 solenoid valves and 2 valves failed in 5 years, this is the quantitative data of probability of failure. So LOPA uses the quantitative data of failure to derive the probability of failure. So LOPA is giving you much precise and accurate assessment of the SIL compared to a qualitative selection of SIL by risk graph or risk matrix. Unlike risk graph and risk matrix, which are more of subjective type of nature, and emotional things can erupt into SIL selection if you are doing SIL selection by risk matrix or risk graph, because it is not very precisely defined. Okay. So LOPA is much better. In USA, people follow LOPA. They don't follow risk matrix or risk graph. In Europe, they still follow, but they say that user has to define the boundaries. If it is a user, it is on the burden, it is on the shoulder of the user. Okay.
In India, we are using the risk matrix more than the LOPA.
India,
is it true, sir?
No. Probably how many people are having SIL verification? Have you verified your SIL? what I want to say is you have to verify the seal before commissioning. You have to first of all validate the against SRIs. Do you have documented risk, documented all documents related to how did you select the seal? If it is properly documented, probably you will have to verify. But verification again needs the frequency of testing to be decided. As I mentioned, SIS is a dormant system. Unless you test it, you will not come to know. What is the document available with you where you have selected your seal by, suppose you have selected seal by 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 risk method. Okay, I tell you, let me show you. Yeah, say this is a seal selection by risk matrix. In this slide, if you have selected seal by, if you know this diagram, then seal 3 is selected. You add one more layer of protection. Say if it is a pressure loop and you add 2 more layer of pressure safety valve, what level of seal it will get reduced? So your knowledge is very important and application is equally important. If your safety relief valve is on clean service and of the full stroke, full flow size, then probably it can reduce the level of risk simple by seal by 2 safety valve to a level from seal 2 seal 1. So this is a risk matrix. This is indicate. These are the seal. These are seal 3. Seal 3 gets reduced to seal 2. Seal 2 gets reduced to seal 1. It all depends upon that you can. Yeah, I want to include computer audio when I'm explaining this. Okay. So if you are, you can reduce the seal by adding additional sea level. The risk matrix, as I mentioned, is not very accurate. So if you want accurate assessment, then you have to go for LOPA only. Unfortunately, one full day is required to cover all the slides which I have prepared for this presentation. And with the limited time, I thought whatever I have tried to tell you was most fundamental. Even before you take any course of any other course trainer, okay, this will definitely be useful to them. But our training is more or less based on safety standard. I think